Okay. Which of the following formulas is an empirical formula? Well, you're looking for the one that you can't factor anything out of the subscripts. So I can factor a 2 out of all these, or I can factor a 6 out of all these. I can factor a 2 out of these. It would just be 4 and 9. I can factor a 2 out of these. It would be 2 and 5. But I can't factor squat out of this. So there is no common factor. So guess what? That is the empirical formula. That is the definition of empirical formula. Oh, and by the way, anything where you see one atom for anything, in a molecule, if it's down to one atom of one thing, that is the empirical formula because there's no way to factor out of one. Okay? All right, 18 is a calculate the empirical formula. I am going to calculate the empirical formula of I have a compound that is 36.48% sodium, 25.44% sulfur, and 38.08% oxygen. All right, the first step, hecto, Wally Kazam. And I make these into grams. So I can erase it. I can just write it again. I don't care. It doesn't matter. 36.48 grams of sodium, 25.44 grams of sulfur, 38.08 grams of oxygen. Now, the next step, I have to go from grams to moles. So I'm going to go from grams of sodium to moles of sodium, grams of sulfur, moles of sulfur. By the way, this is always 1 mole, right? If I write grams, I better write 1 mole on the other side of it. And grams of oxygen. Two moles of oxygen. Oh, it's not O2 because it's in a compound. Okay. So this is 16 per 1 mole. Sulfur is 32.1. Oops, sorry, you can't see that. 32.1. Sodium is 23 grams. All right, how many moles? Okay, so 36.48 divided by 23. That gives me 1.58 moles of sodium. 25.44 divided by 32.1. That gives me 0.79 moles of sulfur. And 38.08 divided by 16 gives me 2.38 moles of oxygen. Oh, hang on. We gotta text somebody. Might as well just incorporate this into the video. It's somebody texting about the video. Surprising. Okay, Danny. Danny, it will be on here when I'm done. Okay, making video now. Okay, now we got that out of the way. Now we divide by the lowest mole total. Divide everything by the lowest mole total. So 1.58 divided by 0.79 equals 2. 2. So that is the subscript for sodium. Sulfur, 1. 2.38 divided by 0.79 is 3. So oxygen is 3. So it is Na. Na2SO3. Na2SO3. Hey, I think we know this substance. Anyway. Okay. Okay. So now we have, all right, where's our sheet? Okay. So now we've figured that one out. Oh, it's below here. Dang it. Where is everything? All right. So we've done 17, we've done 18, 19. So 19. How many moles of oxygen are needed to produce 10 moles of Al2O3? Now we need some boxes. All right. Let's see, where's my, okay, I'm going to do a different problem here. I'm going to do, here's my balanced equation, plus O2 goes to 2 MgO. And I'm going to say how many moles of magnesium are needed to react with 12 moles, yeah, might as well, of oxygen. All right, moles to moles, one boxer. I'm starting out with 12 moles of oxygen. Notice how I drew the O2. This is not O, this is O2. So by rule, these units diagonally to the right have to be the same, must be the same. And the units of my answer, moles of magnesium, and then they back into here, moles of magnesium. Seems like this is the heart of the problem, or the mole ratio right here. Moles of magnesium, 2 moles of magnesium. Comes directly from the coefficients. Moles of O2, 1 mole of O2. 12 times 2 is 24 moles of magnesium. It takes 24 moles of magnesium to react with 12 moles of oxygen. And that makes sense because there are 2 moles for every 1 mole. So there are 2 moles of magnesium for every 1 mole. Okay. I'm going to use that same thing, and I'm going to say for every 50 grams of oxygen, how many grams of MgO can I make? So 50 grams oxygen, how many grams MgO? And that's a big 3-boxer. 1, 2, 3. All right, so I'm given 50 grams of oxygen. And by rule, I know this is grams of O2. And by the grams rule, I know that this is 1 mole of O2. And by the diagonal rule, I know that this is moles of O2. And that's as far as I can go forwards. Now, I want grams of MgO. So these units go in here. Units of the answer, grams MgO, which means by the grams rule, this is 1 mole MgO. And by the diagonal rule, this is moles of MgO. And look, if you don't have moles of one thing that you're looking for over moles of the other thing, then you have made a mistake. There is always a mole ratio, this heart of the problem, right? And in my reaction, there are 2 moles of MgO for every 1 mole of O2. There are 32 grams of O2 and MgO. Let's see, 24.3 plus 16. Oops. 24.3 plus 16 equals 40.3. Okay, now it's a math problem. Now it is 50 times 1, enter, times 2, enter, times 40.3, enter. Oops. Yeah. Uh-oh, battery is running low. Oh, because I unplugged it like a dork. Okay. Hang on, we gotta do some, okay, times 40.3. Okay, and then divided by 32, enter. Divided by 1, enter. Divided by 1, enter. 125.93 grams of MgO. That is how you do a grams to grams. Make sure that it contains a mole ratio, the heart of the problem. And in grams to grams, it's right in the middle. Okay, so that gets us through 19 and 20. And all right, moles to grams. How many boxes? Moles to grams. It's a 2-boxer, right? So we're going to go with, we need another sheet of paper because we're going to use the same balanced equation here. All right, so we're going 2.5 moles of magnesium, and we want to know how many grams of MgO we can make. Does that seem like a reasonable request? Okay. Okay, so we know it's 2 boxes. And we know what we're given. Oops, sorry, let's move you around here a little bit. 2.5 moles of magnesium. By the diagonal rule, we know this is moles of magnesium, and that's as far as we can go. And so we got to start from back here, and we're going to grams of MgO. So those units back into this top spot here, grams of MgO. And when I write grams, by the grams rule below it, 1 mole MgO. And then by the diagonal rule, this is moles MgO. And it is 1 mole, 2 moles of MgO, 2 moles of MgO for every 2 moles of magnesium. And grams of MgO, we just did it a second ago. How many grams are in MgO? 40.3. Seems pretty trivial. I think we can do this. 2.5 times 2 times 40.3, enter. Divided by 2, enter. Divided by 1, enter. Seems like I have 100.75 grams of MgO. That is how we do that. All right, so that is 19, 20, 21. 22, a burning candle is placed in a glass jar. The jar is then closed. The candle burns for a few seconds before going out. At the end of the reaction, the candle is still present. Identify the limiting reagent. So the candle is a hydrocarbon. So candle plus O2 goes to CO2 plus H2O. This is the hydrocarbon in this case, so it's, C4H8, whatever hydrocarbon. And what did I run out of? When I close the jar, I cut off the supply of this. If there's candle left, there's plenty of that. So the limiting reactant, there's only 2 reactants, the candle and the oxygen, and it seems like the oxygens ran out because there's still candle left. All right, in lab, you decide to mix solid zinc with a clear solution, hydrochloric acid. During the reaction, you see hydrogen bubbles. You also determine that a solution of zinc chloride forms. You also notice that all the solid zinc is now gone, but 5 moles of HCl remains. So zinc is your limiting reactant because it's disappeared. Would you just, for the love of God, just stay on? Okay, me and the lights have talked it over. We've come to an agreement. Is the limiting reactant, and hydrochloric acid is the excess reactant because 5 moles of HCl remain. 3 factors that affect the rate of solvation. I'm going to give you the ones the way I do. Shake, bake, break, and I'm hoping that you'll put in like stirring agitation, heating, and whatever this does. What does this do? Do you know? Do you know what breaking it does? Psst, it's something about surface area. Okay. As temperature increases, what happens to the solubility of a gas? Well, we know that in the solubility of a gas, if we look at a solubility chart, where's the solubility chart? Solubility chart! I'm calling all solubility charts. Aha! A stray solubility chart. Yeah. So gases go down as solubility goes down as temperature goes up. All solids go up as solubility go up as temperature goes up. So, of a gas, as temperature increases, solubility decreases. Of a solid, as temperature increases, solubility increases. Sorry, I have the hiccups now. All right. Pressure increases, decreases, or has no effect on the solvation of a solid. Has no effect. Pressure increases, decreases, or has no effect on the solvation of a gas. Increases. The way they put CO2 into soft drinks is they have big high pressure tanks at 2,500 psi of CO2, and then they pump it in. If you pump it in at high pressure, it will dissolve into your Coca-Cola. Solvation versus dissociation. So solvation is what happens to covalent compounds. And so I have a CH4 and I have CH4. Those are too small. Let's make our molecules bigger. CH4, 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 CH4. In solvation, the molecules all separate from each other. So these all go in different directions and are solvated in the solvent of water. In dissociation, I have an NaCl. I have a molecule of that, and it basically falls apart into its component atoms. It falls into a positively charged sodium atom, a negatively charged chlorine atom. This is dissociation. The molecules themselves actually fall apart. In solvation, the molecules just dissolve away from each other, but this doesn't turn into carbons and hydrogens. It just stays a molecule of CH4, methane. This actually falls apart into its component atoms, and they are surrounded. This thing would be surrounded by the hydrogens of water because the hydrogens are positive. This thing would be surrounded by the oxygens because the oxygens are partially negative. And that's what happens in solution. And it makes for a conductive solution. Okay, Batman must drink a cup of coffee each morning or else he is very cranky. Chaos is about to start in Gotham, so you need to help him dissolve sugar in his coffee quickly. What would you suggest? Well, I would suggest that he go back to the page before. And what affects the rate of solvation? Well, if I'm trying to put sugar, I'm going to do one of those 3 things. But you pick which one and you tell me a cute story about what Batman, what Batman does. Okay, Batman's sidekick Robin only drinks Sprite in the morning. He woke up late in the Batcave, so he was not able to finish his delicious drink. Delicious is a bit of a stretch for Sprite, but we'll call it true for him. He knows if he leaves the Sprite on the counter, it will taste flat. Yeah, because it's going to heat up, and the solubility of gases goes down as temperature increases. So what can he do to keep his frosty beverage from becoming flat? A couple things. He can cap it. because you don't want to let any of that pressure out, right? You want to keep the pressure in there. If you let it out, then it just becomes atmospheric pressure, and there's nothing holding the CO2 in that I put in under high pressure. Also, he can cool it. Put it in the fridge. If you put it in the fridge, it'll keep its carbonation. And I have proof of this. So this is my cup. The drink has been in here all day. It's Pepsi. It's been in here all day, but it's been cold all day. And guess what? It is still carbonated. Okay. What is the molarity of a solution containing 90 grams? And okay, I need my other questions. Where are my alternate questions? Okay. So I'm going to say, what is the molarity of a solution containing 160 grams of C12H22O11 and 1.6 liters of water? So I'm making up an alternate problem here. I have 160 grams of C12H22O11 in 1.92 liters of water, liters of H2O. Well, first of all, I have to recognize that this is a molarity question. It says, what is the molarity? What? Oh, sorry, I'm not even on the page here. Okay. Sorry about that, guys. Okay. What is the molarity of an aqueous solution? So what is the molarity of this solution? And the molarity formula is molarity equals moles of solute over liters of solution. Remember, a solution is the solute plus the solvent. So I don't see anywhere where it says grams. I see where it says moles. So first thing I have to do is turn this into moles. So 160 grams C12 H22O11. And I need grams C12 H22O11 and 1 mole of C12 H22O11. Okay, I guess I have some calculating to do. 12 times 12 equals plus 22 equals plus 11 times 16 equals 342 grams. 160 divided by 342 equals 0.467 moles of C12 H22O11. And then I can plug it into the molarity formula. So I have moles over liters, 1.92 liters equals blank molarity divided by 1.92 equals 0.243 more or less molar. Now, your numbers might not match mine. We might be rounding different. It doesn't matter. This is the process for going from grams to moles, and then for putting the moles and the liters into the molarity problem there. So that was number 32. 33, what is the volume of a 2.4 molar solution that contains 176 grams of LiCl? So I'm going to say, what is the volume of a 4.2 molar solution of KCl? Yes. Yes, he is. That makes, I hope you can hear everybody out there. That contains 146 grams of KCl. So, again, molarity formula. So I can't go with grams. I got to go for moles. So I'm going to have to do a conversion. I'm just going to do it right here. Grams KCl and 1 mole KCl. That is 146. And then KCl is 35.5. Plus 39, 35.5 plus 39 is 74.5. 146 divided by 74.5 equals 1.959 moles of KCl. So now I have moles and I have molarity. So I have a molarity of 4.2 equals, I have moles, 1.959 moles over X. Oops, sorry. I'm squirting off screen here. So I have 4.2 molar solution and 146 grams of KCl. I figure out how many moles. That goes up here. I don't know how many liters. That's what they're actually asking for in number 33. What is the volume? And so these two things switch places, right? So it's 1.959 divided by 4.2 equals 0.466 liters. That is it. That is my answer. That is how you get a volume. All right, 34. How many grams of CCl4 should be used to make a, okay, let's see. How many grams of CH4 should be added to a solution to make a 5.2 liter 0.5 molar solution. So again, now they're asking differently. They're asking how many grams of CCl4 should be added to a solution to make 2 liters. I'm going to do it this way. This is my alternate problem. So how many grams of CH4 are needed to make 5.2 liters of 0.5 molar? Well, I have this. I have X for moles, and I know it needs to be 0.5 molar. So that'll give me the moles. 0.5 times 5.2 equals, so I need 2.6 moles. X equals 2.6 moles of CH4. And then they asked me grams of CH4, so I got to do a conversion of 2.6 moles of CH4. Mole CH4 to grams of CH4, and that is 12, 16. I have 16 grams in 1 mole. 2.6 times 16 equals 41.6. 41.6. Oh, again, I'm squirting off the page here. Grams of CH4. So, again, all I did was put it in the molarity formula. Anytime you see molarity, and when you see 0.6 molar solution, you know that's a molarity problem. Plug in the parts that I have of my, so I had 5.2 liters, I had 0.5 molar. I just didn't know how many moles. Calculated how many moles. Plugged that many moles into my conversion. It was just a moles to grams conversion. And I got my answer, 41.6 grams of CH4. Hopefully you'll be able to do the same for 34. And what else we got? Colligative properties depend on the identity but not the number. That's a lie. The number but not the identity. I think we have an answer. That is the definition of colligative properties. They are dependent on the number of solute particles and not the type. What happens to each of these colligative properties when solute is added? Well, we know what happens to vapor pressure and boiling point, and we can describe them the same way. If I have a bunch of water molecules at the top of this solution, sorry about the beeping, but they turn our overheads off every day, and they're free to run into each other. When I get to 100 degrees, these guys are going to start to liberate, right? So I'm going to start to have vapor. I'm going to have water in the form of vapor. But if I add solute, and I'm going to identify this with these little black particles, I've added something that is black. Then can as many of these water molecules actually get free? The answer is no. So vapor pressure goes down. Boiling point goes up. And freezing point. So if I have these water molecules and they want to make this nice matrix, so this is the matrix for ice, and it looks very nice, right? But what happens when I add the solute in here? Oh, dang it. Just give me 2 minutes and I could have finished the video. Okay, if I add solute in here, they get in between the attractions of these water particles. So you know that water has partial positives, partial negatives, and that they are attracted. So the partial negatives on the oxygen are attracted to the partial positives. Well, if I throw solute in here, it gets in between those the attraction of those molecules. So it lowers the freezing point. That's why we put salt on the roads. I'm okay with you just putting arrows. It lowers the vapor pressure and it raises the boiling point. If these guys can't get out of here at 100 degrees, then they will keep heating up past 100 degrees. If you just have pure water, at 100 degrees, you're not going to get it any hotter because the water molecules are going to liberate themselves out of here. They're going to get so hot that they become vapor. That's what happens at 100 degrees. But if I add the solute in here, then these particles can't get out. They can't turn to vapor. If they can't turn to vapor, the vapor pressure is lowered. If they can't turn to vapor, then they just continue sitting in here and heating up. Does that make sense? God, I hope so. Okay, how would you prepare 1 liter of a 4 molar MgO solution? So the idea here is conceptual. You're not dissolving 4 moles in 2 liters of water because it says it's in 1 liter. You're not dissolving 4 grams in 2 liters of water because it says you're in 1 liter. You're dissolving 4 moles and then adding enough water to reach the 1 liter mark. I think I've said it enough in this class. If I put 4 moles of something into a container, so here it is, this is 4 moles of MgO in the bottom of this glass container. Since this is the last problem, let's just get all artistic on this. So I've got a beaker here, and it is 1 liter. It can hold 1 liter. If I add 1 liter of fluid to this, it's going to run out the top, right? So that's not what we do because this stuff takes up room. It may even dissolve, but it still takes up room. So what I'm going to do is add water till I reach the 1 liter mark. That's going to make a total solution volume of 1 liter. 1 liter, which is what we want. So that this stuff that's taking up space, that's just contributing to my 1 liter of solution. And what is a solution by definition? It is the solute and the solvent. That's what 1 liter of solution has to be. So if I'm preparing 1 liter of this solution, it has to have both the water and the solute and be at the 1 liter mark. I hope that makes sense to everybody. I hope the way I did it didn't throw anybody off. I hope everybody does the review because I really want you to get those points. And more importantly, I want you to do well on this Interim tomorrow. Bye-bye.